Hey kiddos, we're back again and we have remote instruction on Friday. Okay, so for you guys, because I have lots of different calendars here. Let's see. For you guys on Friday, you have a work day. Okay, you want to work on your CA, which I handed out on Friday. Or there is a new Delta Math uploaded. We are going to be having another workday on Monday with a review on Tuesday and then a 2-day quiz on Wednesday and Thursday for next week. So just so you guys are aware of what the word is. Okay, but anyways, we have to get to it. Shouldn't take too long. We're just doing one page. Okay, so for this one, it's a continuation of yesterday. So we're going to be finding zeros of a polynomial function by first finding the possible rational zeros and then testing them. Okay, so just a reminder, we need I like these colors. Okay, cute. So we need our constant and we need our leading coefficient. So the constant is -3 and the leading coefficient is 1. So for the possible rational zeros, you're going to take the factors of 3, which are just 1 and 3, positive and negative, and the factors of the leading coefficient, which is just 1. You divide them, which as you can see, it's just 1 divided by 1, 3 divided by 1. So really, this is kind of nice because there's really only 4 possible rational zeros. Now, yesterday we said that we have to look at the degree of the polynomial, which is right up here. It's a degree of 3. Let me highlight that sucker instead. It's a degree of 3, meaning that we should end up with 3 zeros. Okay, so again, I'm just going to start at 1, go to -1, go to 3, go to -3, and yada, yada, yada. Okay, so I'm going to start with 1. And we do have decreasing order, so cubed, squared, linear, and constant. So I can just write those coefficients right here. 1, 7, 11, -3. Drop that low. And then do the backwards check, which is just multiplying. You put that there. You combine, I get an 8. Okay, do the backwards check. Boop, boop. You get an 8. Combine, you get a 19. And then again, you get 19 and you would get 16. So this is not a winner because the remainder should be 0. So let's try another one. Let's try -1. So I still have the 1, 7, 11, -3. So I'll drop this down. And then we're going to multiply. Why did that do that? Clearly, I chose this. Oh, and it didn't even erase it for me. Boo. See if there we go. Ketchup and mustard. Okay, so I get -1. This becomes a 6. Oh, hi, that should be a 6. There we go. Okay, we're going to do another backwards check. Boop. Combine. So this is -6. Combine. You get a 5. Okay, and then again, multiply, you get -5. Combine, you get a -8. So that doesn't work out either. Whoop, whoop. Okay, so let's try another one. So these ones are out. Those are not zeros. Doesn't work out. Okay, let me try a +3. Okay, so I have 1, 7, 11, and -3. Okay, so I drop this down. I get a 1. Multiply, you get a 3. You get 10. Multiply, you get 30. This isn't looking so good either. Combine, you get 41. We can clearly see this is not going to work. And you get 120. Okay, so that didn't work either. So now we're going to try -3. Hopefully this works. I don't know what's going on with my pen. Okay. 1, 7, 11, -3. Okay, bring this down. Multiply, you get -3. Combine, you get 4. Multiply, you get -12. Combine to get -1. Multiply to get 3. Combine to get 0. And there's your donut hole right there. So -3 is a 0. And now we have to find the other zeros, because what we have left over here, we have the 1, 4, -1. So what that turns into is that because we divided by, we're synthetically dividing, so we always decrease by a power. So it's 1x squared plus 4x minus 1, and we're setting that equal to 0 to solve. You don't necessarily need that, but at this point, there's nothing that multiplies to -1 and adds to give you 4. So this one's kind of a tricky one, because you're going to have to use the quadratic formula. So x equals -b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so we're going to plug and chug. -4 plus or minus the square root 4 squared minus 4 times 1 times -1 all over 2 times 1. Scroll this on down. So -4 plus or minus the square root. Now I would put the numbers in my calculator, which is just 4 squared minus 4 times 1 times -1. So you would end up with 20 over 2. Okay, so -4 plus or minus the square root of 20 all over 2, which the square root of 20 simplifies to 2 radical 5. And if you guys need help with simplifying radicals, feel free to ask. I'm more than happy to help you with that. And then what you do from here is you divide both this number and that number by 2. Do not divide the radical 5 by 2, because the radical 5 is directly attached to the 2. So this answer is -2 plus or minus radical 5. So those are the other 2 roots. So we have -2 plus radical 5 and -2 minus radical 5. So if you see here, you wouldn't have been able to find any other rational zeros because there weren't any. Okay, these 2 that we just found are irrationals because they have a radical in them that cannot be, like, it's not a perfect square. Okay, so that's for the real zeros. The last itty bitty part that we're doing here is Descartes' rule of signs, which, okay, so when you have your function, okay, and just your function as it is, what you're going to do to find the number of positive real zeros, you're going to count the number of sign changes, okay, and it's that number of sign changes or 2 below that or 2 below that or 2 below that until you get to either 1 or 0. Okay, so here's what I mean here. So looking at this function, we start with a coefficient of +3. And it has to be in standard form. That's another thing. It has to be in standard form. This is already in standard form. So when we look from here to here, that is a sign change. Okay, it goes from a positive to a negative. Now, So this is 1. Going from here to here, negative to a negative, that's no sign change. Negative to a positive is the second sign change. Positive to a positive does not change, but positive to a negative does. So there are 3 sign changes with the original function. So for positive real zeros, they can have either 3 or 1. Okay, so if the final number is an odd number, then you keep counting down until you get to 1 by odd numbers. So like let's say there were 5 sign changes, then it would be 5, 3, or 1. Okay. Now for the negative real zeros, what you have to do first is you're going to have to change the original function. So we're going to plug in negative x, okay, because that's what it says to do right here. Okay, so we get 3, parentheses, negative x to the 7th, minus 2, negative x to the 5th, minus negative x to the 4th, plus 7, negative x squared, plus negative x minus 3. Okay, sorry, I kind of ran out of room. So I'm going to simplify this. Anytime you have an odd exponent and you're taking a negative number and raising it to that, it will end up being negative. So for 3 times negative x to the 7th, you're going to change the sign so that it's negative 3x to the 7th. Same with that next term. So it's negative 2, parentheses, negative x to the 5th. So that would become a positive 2x to the 5th. Now for the next one, we have minus, parentheses, negative x to the 4th. If it's an even power, then we just keep the sign that it had. So it originally had minus x to the 4th. That's what we're going to keep it as. Same with the next one. We have negative x squared. That's an even power. So we keep plus 7x squared. Plus a negative x is really minus x and then minus 3. So at this point, we want to see how many sign changes there are. So that first one, negative 3 to a positive 2, there's 1 sign change. Positive to a negative, there's the second one. Negative to a positive, that's a third one. Positive to a negative, that's a fourth one. This last one doesn't change. So there's a total of 4 sign changes consecutively. So for negative real zeros, we could have 4 negative real zeros, 2 negative real zeros, or none. Okay, so notice that I decrease by 2 each time. If you're starting with an odd number right here, okay, then your last number should be 1. If you're starting with an even number, your last number should be 0 for the number of real zeros. Okay, let's check this out. So for this one, there aren't any sign changes. So for the positive real zeros, it's kind of interesting because since there's no sign changes, that means there's no real zeros, which helps when we're doing like the possible rational zeros, right? When we do those, you wouldn't check any of the positives. You just check all negative ones. So this rule kind of helps you eliminate some of the possible rationals that you might have to check. Okay, because if there's no positive ones, then don't check the positives. Okay,